Hello, good morning and good evening, everyone. My name is Jing Feng. Today I'm going to hold the TrustML Young Scientist Seminar. Before that, let me hugely welcome our today's guest, Shavi. Shavi is a PhD student at UCSD. Her research revolves around various aspects of trustworthy ML, including explainability, auditing, robustness. Shavi is supervised by Professor Kamalika. She is supported by Paul Powell and Jacob School of Engineering Fellowships at UCSD. To find more about her, you can check her website, 3w.shavi.yadav.org. Hi, Shavi, you can proceed to share your screen and get started with your talk.
Thanks a lot, Jingfeng, for the introduction, and thanks a lot for also inviting me to give a talk here. I'm very, very excited to discuss this work with you all. So let me get started. So you can see my screen fine, right?
Yes, right.
So I'm going to talk about my recent work on a framework for certified auditing of machine learning models. This work is done in collaboration with Michal Moshkowitz and Professor Kamalika Chaudhary. So talking about the work, so let's talk about how ML is today. We all know that it is pretty much a black box. The data, the training, all these processes make it very hard for us to understand, like, given an input, what will the output be? It's sort of unpredictable. Then secondly, the trend these days is towards large ML models, right? Billions and billions of parameters. And usually what people do nowadays is to take those large models and fine tune them for their tasks. So you don't know what is the original, like how good is the original model? Is it fair? Is it private? Is it accurate? Like most of these questions, we just trust the large model in some way. Then thirdly, the models are proprietary, right? So a lot of them are proprietary. So you only have API access to the model. You've not tested whether it's good or not in any way. Then a lot of people have been making false claims maliciously, or like very naive, unverified claims about their machine learning models. And then lastly, ML models are being used for very critical applications these days. So thinking about the urgency, the government is making a lot of policies like the right to explanation and the right to data deletion by GDPR. And once you have these policies, you want to be able to test the models, right? And you want to be able to find out if a model is good versus not. So that's the need for auditing, I would say. I have written the Japanese term for auditing. I'm not sure if it is the correct term, but probably you guys can tell me. So auditing is, you might have heard of it in the context of tax audits or financial audits, basically. So auditing is a third-party examination of a process in an industry or of an algorithm, and in our case, of a machine learning model. And this examination is for compliance with some norms or policies. But the interesting thing here is the third-party access to something hidden, to a process or something. So we have machine learning models we want to audit. A lot of like work has been done, not a lot, but like some work has been done on auditing. But what is the issue that we are trying to solve? So now auditing has become a very crucial aspect, right? Suppose there's a large company has made a model, and the government wants to test if it's accurate or if it's fair or not, right? And suppose that the government as an auditor says that your model is not good, you will have to stop using it. Then the large company can question back, like, why should I trust you, right? Like, what are the guarantees that you as an auditor are providing me? So that's why, like, since auditing is becoming very crucial, we want to build trustable auditors, which can certify their performance and give guarantees. Any questions so far about the general setup? Okay, so I will proceed. If you have any questions, please feel free to stop me at any time. So now I will define what is the framework that we are proposing and what are the entities in an auditing process. So the first one is the model to be audited. And this model belongs to a hypothesis class that is known to us. The next thing is the auditing property, or AP in short. So auditing property can be something like fairness or accuracy or privacy. It's basically the thing that you want to audit the model for. The next entity in the auditing process is the data scientist, and it can be a large company or whatever, but it basically is the creator of the model and has white box access to the model. So the data scientist knows what are the weights of the model. And for this presentation, we will assume that the data scientist is truthful and honest. And the next entity of the audit is the auditor. So auditor audits the model for the auditing property, and the auditor only has query access to the model. So the model is hidden from the auditor, and it can only do queries through the data scientist. So that's why you want the data scientist to be truthful. And now I will define some properties here, some entities here mathematically. So the first important property is the auditing property. And we define it using a score function, which goes from the hypothesis class to the, which takes a function from the hypothesis class and returns a value in 0, 1. A real value in 0, 1. And then the auditing property, the score function basically encapsulates to what extent the auditing property is followed by the model. So if we are testing for fairness, then S of H would test how much the model is fair or how much it is unfair. If it's privacy, then how much the model is private or not. That is encapsulated in the score function. And then the exact form of the score function S depends on the auditing property. Any questions here? Okay, I'll go ahead. So now we define what is a good auditor. So the goal here is to mathematically define what we would call a good auditor, and then to build auditing algorithms that obey those guarantees or certificate. So to define that, first we consider the auditor's response, which is YA, and we consider it to be a binary variable, yes or no. And this is our definition for a good auditor. So an auditor, we call an epsilon delta auditor. If we call an auditor an epsilon delta auditor, if the score function is very high, for example, if the model is very fair, then the auditor should say that, yes, the model is fair with a high probability. And if the model is totally unfair, then the auditor should return a decision saying, no, the model is totally unfair with probability 1. As an example. So if it is for privacy, then if the model is highly private, then it should say yes, otherwise it should say no. So this is our guarantee for a good auditor, and then we will design auditing algorithms that obey these guarantees. And this can change based on this guarantee can change based on your application or your needs, but we are just providing like one example of what it would look like.
So I have questions. Why why the score function is 0, then the probability is no is equal to 1. That means absolute things.
Yeah, so it is like if it is totally like not following the auditing property, like if the auditing property totally doesn't exist, then you are definitely going to say 1, and you're definitely going to say no with 1. And I'll give examples later which will make it more clear. But
Okay.
like the point is that between 0 and epsilon, it's very hard. But if it is like for surely 1 or 0, then you can say a lot.
Okay. Got it.
So now we will define the protocol of the auditing process. So at each point, at each time point, the auditor picks a new point and queries from the data scientist. The data scientist returns a label and an auxiliary information to the auditor. Now, this auxiliary information can be anything based on what you are trying to audit, but in our case, we consider it to be explanations. And then the auditor gets the label and the explanation, and then it decides whether it should stop or not. Now, if it decides to stop, then it returns a decision which belongs to yes or no. Otherwise, it continues to the next time step, picks a new query, and so on. So just to show it pictorially. So auditor picks a data point, sends to the data scientist returns a label and an explanation to the auditor. Auditor thinks, should I stop or not? If yes, then it returns a decision. Otherwise, it goes to the next time step. So now the first thing is, how does the auditor pick a new query? Then like I'm trying to define like what are the degrees of freedom that you can use to make different kinds of auditing algorithms using our protocol. So the first point is, how does the auditor picks a new query? Then instead of explanation, what other auxiliary information can you use? And thirdly, auditor has to somehow decide whether or not to stop, right? So how does the auditor make that decision? That will determine the query complexity of the protocol. And like based on how you change these 3 things, like how does it pick a new query, what auxiliary information it uses, and how does it decide whether or not to stop, you can create new algorithms for the auditor, which can satisfy the guarantee that I described earlier. Any questions here? Okay, I'll proceed. Yeah, then now I'll give an example of auditing for a particular property using the things that I described earlier. So in our use case, we are thinking about auditing feature sensitivity. So feature sensitivity is the question, is a feature being used to make a prediction or not? Like that's the basic question that we want to audit for. So we consider a feature of interest. For example, if your age is greater than equal to 35, or what is your gender, or any binary variable for right now, that can be a feature of interest. And you want to know if this feature of interest is being used by the hidden model or by the data scientist's model to make a prediction or not. Then the next definition that we need is pairs of data points. So pairs are data points which have all the same features except the feature of interest. So here, as you can see, like the red and the orange are age features, for example, and the other 4 features are same, but just the age feature is different. And the next definition that we need is responsive pairs. So if the model has different predictions on the pairs of data samples, then we call it a responsive pair. So the model responds to the change in feature of interest. That's why we call it a responsive pair. And here you can see, like, if the model's prediction is different on the pairs, then it can only be due to the feature of interest, right? Because all the other features are the same. So the only difference in the prediction is because of the feature of interest. Now, what is the auditing property in this case? So the auditing property is, in simple English, it is the sensitivity of the model to the feature of interest. That is what is the auditing property. And equivalently, we can say that is there the existence of respective responsive pairs with respect to the feature of interest, right? If these responsive pairs exist, then you can say that the feature is being used to make a prediction. So S of H is the fraction of responsive pairs, or it's the probability that a pair is a responsive pair. And S equal to 0 means that there exists no responsive pairs, and hence there is no feature sensitivity. And S equal to 1 means all pairs are responsive, and hence there is complete feature sensitivity. Any doubts regarding this?
I have a questions. For this part, this give me the feeling that it's related to the explainability, like sensitivity of the model to the feature of interest. What the differences between here the auditing the feature sensitivity as explainable research?
So in the explainability literature, you have white box access. You are the data scientist and you are trying to find the explanations. But here in auditing, you don't have access to the model. You don't know what is the real model. You just have API access.
I see. It's black box. Got it.
Yeah, so I'll proceed. So now we have defined our protocol, our framework, and we have grounded all that in or trying to audit for feature sensitivity. And we know what is the auditing property when you want to audit for feature sensitivity. Next, I'm describing a baseline algorithm for auditing, which does not use any of the stuff that I talked about. So what would you do if you were to test for feature sensitivity? Like you can have set of all pairs, and then you pick pairs randomly and query, right? And as soon as you find a responsive pair, you can stop and return a decision that yes, the feature is sensitive or whatever. But if, as you can imagine, the number of pairs that you need to test for changes with S of H or epsilon, because if the feature sensitivity is very, very low, or if there is only one responsive pair, for example, then you have to test a lot of pairs before you can find a responsive pair in the worst case. So this is a problem because it's not exploiting the structure of the hypothesis class. Like this algorithm is constant, whether it's for a neural network or for a linear classifier, the algorithm is the same, right? You just pick pairs randomly and you query. But if maybe you can do better by exploiting the structure of the hypothesis class, and if you use something more than the label itself. So next we will see how our auditing algorithm, how our auditing protocol works by exploiting structure of the hypothesis class and using explanation. But before that, I need to explain a little bit about what are local explanations that we are using in the paper. So there are different kinds of explanations, but what we are using are local explanations, and local explanations tell us how the model behaves locally around a given point. So one such local explanation is counterfactual explanation. So given the point X, what's the closest point, but with a different label? So here you can see the red is the given point and the purple is the point which is closest to it, but different from different label than X. And here I'm assuming the closeness is measured by a Euclidean norm. And similarly, another explanation that we're using is anchor explanation. So anchors, given a point X, anchors are rectangles around the point where everything has the same label. So given this point X, everything in the a rectangle in purple has the same label, right? So that is anchor explanations. And we are going to use counterfactuals and anchors in our work. So now I'll describe some of the results that we got, and we are going to define them, describe them for linear classifiers. So for linear classifiers with counterfactual explanations, you only need one query, one random query to audit. So given the point X, so the auditor picks any random point X and it gives to the data scientist. The data scientist returns the label and the counterfactual explanation X dash. And using this too, you can find X minus X dash, which is parallel to the weights. And that's why, like here, what you want to know, using this, you can know if the weight of the feature of interest is 0 or not. If the weight is 0, then you know that the feature is not being used, right? And if the weight is non-zero, then the feature is being used. And here, just because of the structure of the linear classifier and the definition of counterfactual explanations, using just one query, you are able to find if WI is equal to 0 or not. And hence that's enough for you to audit. And we show for anchor explanations, in the worst case, anchor explanations will not help you any more than the labels that you get themselves. But when you have average anchors, they will help you. And we show that experimentally in the paper. Yeah, so any questions regarding this?
Yeah, I have a question. Why the worst case explanation does not help with anchor explanation?
Yeah, so this whole anchors thing works on reducing the search space over hypothesis. So when you see that, like the worst case anchors are basically they don't help you reduce the search space by any more amount than the label themselves. So the reason for that is like, it's a little bit complicated, but it's simply that like you have a search space over hypothesis and you are looking for the correct hypothesis that the data scientist has created. When you use labels versus when you use labels plus worst case explanations, the search space is not getting reduced by any more amount, like it's the same. And that is because basically like the worst case anchor is a degenerate rectangle, like it's a ray basically. And yeah, I can tell you more, but like that's the main reason.
Okay, thanks.
Jingpeng, I think there might be a question in the chat and I'm not able to read it. If you can read it for me.
Yes. Hi, Zhao. Can you open your mic to
Oh, yes. My question is that I'm wondering the goal of the research of auditing. Is it building a trustful or fair third-party auditor? And if so, is it the reason that the auditing tool developed from the research can be applied practically? For example, the GDPR office has a tool to supervise the big companies' models that deployed in Europe. Is that right?
Okay, thanks for your question. So the goal of this research is to indeed to build auditors which can guarantee that they are going to give you the correct answer. So so the goal is to build a trustworthy auditor, as you said. Yeah, so that like because auditing is like using, if the auditor says that the model is, for example, unfair or the model is not private, then it can ask the large company which is building the model to stop using it, right? So this large company can question back, like why should I do it? Like, what are your guarantees? Why should I trust you as an auditor? So that's where like you need an auditor which can certify that whatever I'm saying is correct.
I see, because my question is derived from Jinfeng's previous question about the explainability. So we can view that explainability is a research that a company can conduct inside the company.
Right.
And for auditing, it is it can be looked like a social tool that it gives a kind of assurance to the government and the company.
Mm-hmm. Yes.
For the fairness or to make sure the secure of the model for practical use, right?
Mm-hmm. Yes.
I see. Thank you so much.
Yeah, and the point here is that while explainability is being done by the creator of the model themselves, this auditing is being done by a third party, and auditing is, the auditor does not have access to the model. It's black box. So that's how it's
for business purpose that.
Right.
I see. Thank you so much.
You're welcome. Any more questions? Okay, so now we have defined a protocol, we have a guarantee, we have an algorithm, we have algorithms that use counterfactuals and anchor explanations and give you trustable auditors. Now, the goal of this research is, like if you see in the paper, the goal is to reduce the query complexity to achieve those good auditors. That is one of the goals. So with counterfactuals, you only need one query, and with anchors, you need log of 1 by epsilon sort of queries to be able to audit. Now I'll discuss, I'll take a little bit of a detour and discuss how active learning and auditing, that as we mentioned in our paper, are connected. So for that, I will have to introduce the notion of query synthesis active learning. It's a big name, but it's very simple to understand. So basically you have an active learner and an oracle. So the goal of the active learner is to learn the hidden hypothesis. And the way it does that is to generate a query and give to the oracle, and then get the label from the oracle to be able to learn. So usually what you have is a data set of points, right, with X, Y, like both of X, Y in supervised learning to be able to, and then you find like how you minimize the loss function, and that's how you learn. But here the goal is to learn with as few queries as possible. So you only choose, you actively pick up some queries, but not all, which will help you learn. So there are different types of active learning, but the one that is of our interest is query synthesis active learning, wherein the active learner generates new queries and then asks the oracle for the label, and then the oracle gives back the label, and then the active learner can do like optimization using a gradient step or something using that. So if you think about our framework, it's kind of similar to active learning, right? Because the auditor is also generating queries of its own and then giving to the data scientist, and data scientist returns the label and the explanation. Now, the connection is that if you have no explanations, or if you have useless explanations, like in the worst case anchors case, then it's like kind of similar to active learning. And I'll also discuss how it's different. So it's kind of similar. Now, but if you see, like the goal of active learning is to learn the hypothesis, right? Whereas the goal of auditing is to be able to give a decision, like yes or no in our case. The goal of auditor is not to learn the hypothesis in any way. But learning can be one way to audit. Like if you go deeply into our paper, you see that for anchors, we are basically using active learning itself. So learning can be one way to audit, but yeah, so using this intuition, we propose that if there exists a membership query active learner that can learn the data scientist's hypothesis in T queries, then it can also audit in T queries. So it can use the active learning algorithm is the same as the auditing algorithm, and it can use that. And that's based on the intuition that learning can be one way to audit. And this can be simply seen as like, if you know, initially the model is hidden from the auditor, right? But when it knows H bar, it can, theoretically, it can compute S of H bar, and that should give you the decision. But learning may not be the only way to audit. So what we propose is that there are active learning algorithms and there are auditing algorithms, and active learning algorithms are a subset of auditing learning algorithms. So yeah, so auditing can be done using active learning algorithms, but there can be way smarter and better ways to audit instead of active learning that you could use. As an example, like in the counterfactuals case that I mentioned, you, or in feature sensitivity, for example, you just need to know what is WI for linear classifiers. You just need to know if WI is 0 or not, right? You don't need to know what are the other W's or what is the bias B. So you only need to know what is WI. And using counterfactual explanations, when we audit, we are not learning B, and we are only learning a scaled version of the W's. So it's sort of partial learning. And I realized some time ago that our approach is a bit suboptimal, and there are better ways which will only give you WI and nothing else. So basically, partial learning can be enough for auditing. Yeah, so these are the connections with active learning. So if anybody has any questions, I'll wait for a minute or 30 seconds.
Yeah, I just want to add something kind of like black box attacks. They could be also used in the auditing algorithms besides active learning, I guess. Yeah.
Yeah, that is true.
Have you tried that? Like the black box attacks or something? Yeah.
Yeah, I've thought about it. So black box attacks can be actually useful. But I know of some attacks which like try to learn the model also, like try to approximate the model using API access or something. So that might be similar to active learning, but there can be like other sorts of black box attacking methods which can be useful here.
Yes, okay.
But the black box attacker, one difference can be that the black box attacker doesn't care about what other information it's getting. But here, the goal of auditing is to not learn anything more about the model than what is required. Like our approach is a bit suboptimal, but I think you can come up with smarter ways where you don't reveal any more information except what you need for auditing.
Okay.
Like black box attacker might try to extract like more information, or it does not care about what is the extra information. But here we do care that no extra information is revealed because the models are proprietary.
I see. Okay.
Yeah, and another difference is in the intent, like when you define, so we are the ones creating auditing algorithms, right? And these auditing algorithms like are not maliciously intended, but those black box attacking things might be malicious, or people can use auditing algorithms for maliciousness also. So maybe, yeah, that's not a good difference.
I see. Okay. Thank you.
Anyone else has any questions? Okay, so I'm at the last or second last slide here. So to conclude, we've given a theoretical definition and framework for what we call certified auditing. And this work can also be seen as a new use case for explanations, right? Because we used counterfactual and anchor explanations for auditing, which has not been done before as far as my knowledge goes. And they indeed help us a lot of times to reduce our query complexity. And we also here, we see like the difference between different kinds of explanations. So we saw that counterfactuals were very useful while anchors were not that useful. Then another contribution of this work is to describe connections with active learning, which I think is interesting and also important. So the takeaway from this section was that active learning algorithms can be used for auditing, but there exist smarter and better algorithms which either do partial learning or don't need learning, as far as my intuition goes, for auditing. And if you read more, then in the paper, you'll find sections about how to deal with an untruthful data scientist and some experiments that we've conducted on tabular data sets. Yeah, here are some references, and that's all.
Yeah. I have a question.
Mhm.
Based on my previously question on connection between the active learning and black box adversarial attacks, it give me the feeling that if suppose we really want to use the black box attacks, we need to have some constraint on the black box attacks, kind of like a modified version of black box attacks. Some constraint, because for example, some features, but for the active learning, yeah, there should be have some constraint. Can you explain more about technically how the active learning is applied to your approach, in your framework? Yeah. So with some constraints.
So the way,
yeah.
The way I see it is that, like theoretically, if you have a closed form for function S, like here, if you have a closed form for your S, if you can mathematically write it down, then if you plug in this H, then you will get a value for the score function S of H, right? And you can learn this H using active learning, which will reduce your queries. So that's what I was thinking, but I don't think there are any constraints in active learning as such. So my connection just comes from basically this picture. Like it's very similar to active learning.
Yeah.
And that's why, and that's why, like, I have a very, like, this result, like the last line, it's very theoretical. Like if you can compute, if you can find your H bar using an active learning algorithm, and if you know what is the closed form or something of S, then you can compute S of H bar, which will give you the auditing decision. Yeah, you were saying something.
Yeah. Yeah, give me the feeling that, yeah, you want to learn H bar is kind of like a hypothesis, right? Yeah, this also gave me the feeling that it's more like some model extraction attack.
Yeah, but what this is, like, our approach that we use in this paper might be similar to that, but what we are also proposing is that, like, active learning is only a subset of auditing. Like there can be smarter ways, you know, for auditing. So for example, in feature sensitivity case, you just want to know WI, right? Where I is the feature of interest for linear classifiers. So instead of like doing all this active learning thing, what if you can ask the data scientist, what is the dot product of your W's with a one hot vector which has one at the ith location, right? So if you can ask, like, instead of asking queries and all that, if you just ask the data scientist, what is the dot product of your weight vector W with a one hot vector which has one only in the ith location. So if that dot product is non-zero, then you know that the weight is that the feature is sensitive. If it's 0, then you know that it is not sensitive, right? So here, like, you are not doing any sort of attacks, for example, and you're also not doing active learning. So this is a very smart algorithm that can help you audit just using one query, but it's a different kind of a question.
Yes, I know this.
Mhm.
Yeah, I got it. The follow-up question would be,
Mhm.
how smarter it is technically for
Mhm.
active learning. Why this method is superior than others in what
Mhm.
aspects?
Yeah.
Technically.
So the way it is smarter is that it's asking different kinds of questions. So you can use your queries like data points. You can query and try to find what is WI. Or you can directly ask a smarter question like, what is the dot product of W's with this one hot vector? So I think the difference is in the kind of questions that you can ask.
Right. That means that query should have as much diversity as we can to
Mhm.
cover the true functions.
Yeah.
This is kind of active learning. I have done some experiment on active learning using the Bayesian things.
Mhm.
They kind of like they minimize the bound, optimize the bound, and the exploitation, like something just recover the black box function by
Mhm.
doing the as few query as possible. Yeah, yeah. Give me feeling that this can be really used in the model extraction. But there are already recently there are already many research on doing the model extraction, but actually they are not applying those model extraction method do not apply the active learning method. But now you are doing auditing, you apply the active learning method to do this. This is very, very interesting, I think. So
I
yeah,
want to say something.
yeah.
So I understand.
Yeah, what advantage? Yeah, so compared to other people's way of doing extractions.
So the point that I'm trying to make here is that you may not need to do active learning. Like, learning is one way to do auditing, but there are smarter and better ways of auditing. Like, learning is not necessary to be able to audit. Like, that's the point that I'm trying to make.
Yes, I see.
So you are saying that you can do active learning and audit, you can use active learning to do auditing in better and query efficient ways. But what I'm trying to say is, yes, you can do auditing using active learning, but you may not need active learning, because the goal in active learning is to learn the hypothesis, right? But our goal is to give a decision. So you may not need to learn the hypothesis. For example, if you look at this guarantee, if you look at the guarantee here, so usually you have a search space over hypothesis, and you reduce the search space to find your H bar, which is the data scientist's model. Now, suppose at time t dash, you have 5 hypotheses in your search space, okay, left, and all these hypotheses have S of H equal to 0, or all of these have S of H greater than epsilon. Then you don't need to know what is the true H bar, right? Because all of them have the same all of them have the same score function value. So you don't need to know what is H bar, and you can directly give a decision yes or no, because all of them have the same value. So you don't need to recover like what is the true H bar. So what I'm trying to say is, like, you probably don't need active learning or learning in general to be able to audit. You can do some smarter things, because active learning, like for some hypothesis class, it's useful and the query complexity is low, but for other hypothesis class, like the query complexity is as good as passive learning. And I'm trying to say that you can do auditing without using active learning or without using learning.
Yeah. Oh, I see. Yeah. Okay. Then I have another question is, what is the difficulty of the auditing across different model, different task? They should have a different levels of difficulties of auditing different tasks or different models. What do you think? Yeah.
So one difficulty comes from the hypothesis class itself. Like, for example, for linear classifiers, you already know, like, if WI is 0, then the feature is not sensitive, and if the WI is non-zero, then the feature is sensitive. But can you say something like that for neural networks? No, right? Like, because they are more convoluted, so you cannot say that. And that is just for, even for feature sensitivity, you don't have a clear-cut answer. And like, so with privacy and with data deletion and with all the other fairness, for example, like, you don't have a clear, explicit way of saying something using weights.
Yes. Right.
So that is one difficulty. And yeah, so like the goal is to find, like in the diagram that I'm showing, I hope, like, we know algorithms in yellow that can be used for auditing, but my hope is that we can discover algorithms in the blue region, which are not known. And those are more difficult.
I see. Okay. Yeah, I think that is all my questions. Yeah, hi audience. Do you have more questions? You can open your mic to ask Xavi.
This can only happen if I did a very good job or if I did a very bad job.
This is quite open, and everyone can ask questions, and we facilitate discussion and facilitate ideas. That is the purpose.
Yeah.
I think you did a very great job. This is actually very interesting problem. I think this deserve a lot explorations.
Thank you. Yeah, indeed, like, this is almost the first, or probably one of the first works that connects that to active learning and shows, like, what are the possible directions that you can explore. There are lots of open directions in this field. And if any of you have doubts after this, please visit my website, which is chaviyadav.org, and you can email me or set up a time for chatting about this more. And hopefully, if you want to collaborate, that's also, I'm open to that.
Okay, sure.
And that's for all of the audience.
Yeah, okay, great. All right. Then if no further questions, thanks again for Xavi's great talk. Then our next talk gonna happen at 10 o'clock. That means that 10 minutes later. Our next speaker, Anaya, will come soon. So we can wait slightly minutes and get relaxed for 10 minutes. Yeah. Okay. Thanks again for Xavi's great talk. We sincerely welcome her to give us talk today. Thank you, Xavi.
Thanks a lot for inviting me. It was very nice to give this talk. I hope it was in person, but yeah, this is also great.
Yeah, I think when you have a chance to visit Tokyo, you can come to our center. In Japan is in the center of Tokyo, near Ginza place. Very nice place. You can come to visit us.
Thanks a lot. And I also wanted to share my slides if just with other people.
Sure, no problem.
So I'll send the slides to you and maybe you can post it to the group or something.
Sure.
Thank you. See you all. Bye.
Yeah, let's get relaxed. Around 10 minutes. Take a break. We will have another talk at 10 o'clock. Ananya is a PhD student at Stanford, working with Percy and Tengyu. Hi, Michael. Nice to meet. Nice to see you again.
Hello.
Yeah, great. And I think Michael is also in Stanford, working with Percy and Tengyu. You guys can get started at any time you want.
Great. Yeah, thanks a lot for the introduction, and thanks everyone for coming. So I'm Ananya and this is Michael, and I'll be talking about understanding and improving representation learning for robustness. So here's a pipeline for robustness that's been very successful recently. So first, a rich organization like OpenAI or Google pre-trains a model on tons of data. Then after that, everyone can cheaply fine-tune the model on labeled examples that they have, which may be from one distribution. And it actually does pretty well out of distribution too, which I'll talk about. And finally, you can improve your model by doing some post-training things like self-training or ensembling and stuff like that, which I'll also talk about. And our goal is to improve and understand these methods for robustness. There are some messages, but I can't see them. So, oh, I guess, yeah, feel free to ask any questions. Just stop me. Okay, so first I'll talk about the fine-tuning step. So if we have a large model, how should we fine-tune it for robustness? So this is based on work that we presented as an oral at ICLR recently, and it's with my collaborators and advisors. So in classical ML, we have a data set and we train a model on that data set. So for example, we might have a satellite remote sensing task. So given a satellite image, you want to know what's there. And we may have in-distribution training data from North America, and we train. But that's not how things work in modern ML. So in modern ML, we start with the pre-trained model, and the pre-trained model takes in inputs and gives you features. And we adapt it for the task at hand. So we take that model and we adapt it for the remote sensing task. And this does much better than training from scratch. Okay, so now we've taken our model and we've trained it on in-distribution training data from North America. And we might test it on held out examples, test data from North America. But we might also want to see if our model's robust, if it's learned the right thing or it's overfitting to North America. And so we might want to test it on out of distribution test data, say from Africa. So note that this OD test data, it's not used for hyperparameter tuning. It's not used for fine tuning. It's only used at test time to see if the models learned something reasonable. So our question is, how should we adapt pre-trained models like CLIP or SimClear on in-distribution training data when we want to learn something that's more robust and generalizes beyond the training data? Okay, so there are two standard methods that people use to adapt their model. So we have a pre-trained model that takes in inputs and outputs features. And you need to use these features for a task. So like given a satellite image, you're trying to predict something about it. So you have to add a head. So usually this head is either randomly initialized or initialized at 0. And fine-tuning then backpropagates through the entire model and does gradient descent. Whereas linear probing freezes the pre-trained model and only tunes the head via backpropagation. So there are many methods that people use in practice, but these are the most popular. And so out of these two, which method does better? So we evaluate both methods on a wide range of data sets. So these include things like style shifts in DomainNet, or different species of animals, and also real-world satellite remote sensing data sets where we test on different countries. And common wisdom is that fine-tuning works better than linear probing because you can update the features for your task. And indeed, in the in-distribution test set, we find this to be the case as well. Fine-tuning does better than linear probing. But in the out-of-distribution test set, so this is out-of-distribution data that wasn't seen during fine-tuning. So on this OOD data, fine-tuning often does worse. So it got about 7% worse on average, and it did worse on 8 out of 10 OOD data sets. And so the starting point of our work, the starting observation, was that fine-tuning can often do worse out of distribution, especially when the pre-trained features are high quality and the distribution shifts are large. Okay, so we've seen that fine-tuning can do worse than linear probing, OOD. And in our work, we first tried to understand why fine-tuning can underperform OOD. And based on this theory, we propose a simple change to fine-tuning that gets improved accuracy on all 10 distribution shifts. So let's start by explaining why fine-tuning can underperform out of distribution. By the way, is everything clear so far? Like any questions that people have about the setting or the methods? Okay, let's jump ahead. Cool. So let's say we have good pre-trained features. So in this figure, blue represents in distribution examples, green represents out of distribution examples, and the circles and crosses are different classes. So let's look at what fine-tuning does. And remember that fine-tuning is only done on the in distribution blue examples, not on the green examples. So we start out with the head that's randomly initialized. And the goal is to separate the blue circles from the blue crosses. So we update both the head and the features via gradient descent and try to separate the blue circles from blue crosses. So during this process, the features for the ID examples change, but the features for the OOD examples don't change as much. So as we're running gradient descent, the head changes and tries to separate the blue circles from blue crosses, and the features also change. And eventually we're happy. We've separated the blue circles from the blue crosses. In this process, the features have changed for ID examples, but not so much for OOD examples. And we call this feature distortion. And you're doing well ID, but now because of this rotation, the head performs poorly on OOD examples. So that's the story for fine-tuning. That's why fine-tuning can do poorly out of distribution, because it changes these features in an inconsistent way between in distribution and out of distribution. What about linear probing? So if we had good features, linear probing, well, it just freezes the features. It only trains a head on top. So in distribution, linear probing is not able to improve the features. So if the features you were given are not perfect for the satellite remote sensing task you're trying to solve, then you'll make some mistakes in distribution. But on the other hand, you can extrapolate better out of distribution if the features were good. So you don't have this distortion issue. So in our paper, we proved this formally for two-layer networks. I'm not going to go over the theory, but if you're interested, you can look at the paper or ask me questions. And one thing to note is that fine-tuning is non-convex. So the trajectory is complicated, and there's no known closed form, even for two-layer nets. So like two-layer nets might seem really simple, but it's actually pretty hard to analyze mathematically. And what we showed is that out of distribution, fine-tuning does worse than linear probing under two conditions: if the pre-trained features are good and the OOD shift is large. And this happens throughout the process of fine-tuning. So not just at the end, but throughout the trajectory while you're fine-tuning, it does worse. On the other hand, in distribution, fine-tuning does better than linear probing because it can adapt and improve the features for the task. Okay, so far in the intuitions, I assumed that we had good pre-trained features, and that's a key condition. So we're not saying that fine-tuning will always, whenever you have an ML system in the world, fine-tuning will do better. A key condition is that the initial features have to be good for both ID and OOD. And we'll talk about this in the next part of the talk, about how you can learn these good features. And we've done a bunch of work on this. But for now, let's press on the fine-tuning story. Okay, so we have a theory for why fine-tuning can underperform OOD. So can we fix this problem with fine-tuning? So far, we've seen that fine-tuning does better on the ID test set, but linear probing works better on the OOD test set. So we have this trade-off, which isn't that desirable. And the reason fine-tuning doesn't do well OOD is it starts with a random head, and that head is not very good to begin with. So it changes a lot. And during that process, the features get distorted as well and change a lot. So can we get the best of fine-tuning and linear probing? So can we get the benefit of fine-tuning that you can improve the features for ID, but not have this distortion? So one idea is to use Lpfd. So this method has been used as a heuristic in prior work, but not for robustness, and there's no analysis. And it's a simple method. So first you linear probe. So you train a linear classifier. And then you fine-tune. And the intuition for why this works better is that when you linear probe, you get a good head classifier. And now the head classifier doesn't need to change much. And so the features, the ID features, don't need to change as much. So they get distorted less. And we prove this intuition in a simple setting in our theory. Okay, so all that's the theory, but how does this work in practice on real deep neural networks? So we consider standard data sets, including CFAR, ImageNet, DomainNet, breeds, satellite remote sensing. And we consider both ResNets and vision transformers. We also have a rigorous experimental protocol. So we tune all hyperparameters only on ID validation data, not OOD data. And when we sweep over learning rates and do early stopping. And we also ensure that Lpfd and fine-tuning use the same amount of computation. So Lpfd has 2 stages, linear probing and fine-tuning, but we make sure to run each stage for less time so that both methods use the same amount of compute. So as an executive summary, this simple change can improve things dramatically. So in distribution, you get slight improvements over fine-tuning. So the accuracy goes up from 85.1 to 85.7, averaged over the data sets. But out of distribution, there's a huge improvement. So it does better than both linear probing and fine-tuning, and it does about 10% better than vanilla fine-tuning. So going into more details about the results. So for the in-distribution test sets, Lpfd does better than fine-tuning and linear probing on 5 out of the 6 data sets. On one data set, Lpfd is in the middle. And we think that might be because for FMO, which is a data set where it's in the middle, the initial features are not that good. The accuracies are about 50% to begin with, And so the features are likely not that good. So Lpfd can't leverage the linear probe as well. Out of distribution is where the method really shines. So across the board, across all the 10 data sets, it does either comparably or better than both fine-tuning and linear probing. So it quite consistently does really well. So more recent follow-up works by other groups, not by us, have also used this as a component in their method. So state-of-the-art methods usually have multiple pieces that are required to get high accuracy. And in this paper by Wartzman et al., they fine-tune this big VITG model that's pre-trained on JFD. They fine-tune it many, many times with Lpfd. And then they average their weights in a greedy strategy. And this approach gets state-of-the-art on a wide range of data sets, regular ImageNet, wilds, ImageNet robustness, etc. So it suggests that this thing that we've proposed can also, for robustness, can also be integrated into bigger, broader pipelines to get state-of-the-art accuracies. Okay, so a good theory should also explain why things are happening, right? So we had a feature distortion explanation for why fine-tuning doesn't do so well OOD, but we want to test this and make sure that's what happens in practice. So the first thing our theory predicts is that the features for ID examples change more than for OOD examples. That's why the feature distortion happens. And indeed, we see this to be true across the data sets, and the exact numbers are in our paper. So the next thing we predict is the reason Lpfd works. So our theory says that Lpfd works because when you start with a good head, the features don't change so much. There's much less distortion going on. And indeed, we find that when you do Lpfd, the features change orders of magnitude less. So it's between 10 to 50 times less, depending on the data set. So finally, our theory applied throughout the course of training, not just at the end of fine-tuning. And so one thing you might ask is, with fine-tuning, like if you early stopped it, if you took the model at some point earlier in training, does it do better than linear probing? So is it just that you're training the fine-tuning so long that it overfits to the distribution? And so what we found was that in many of these data sets, at no point in its trajectory does it do better than linear probing. So it's not a simple story of like, you can just fine tune a little bit so you don't overfit too much to your ID. One thing I should emphasize is that our theory and our paper have key conditions. So we say that fine tuning does worse than linear probing if the features are good and the distribution shift is large. And that's what we proved. And we ran a few ablations to check this. So on the 2 out of 10 data sets where the shifts are much smaller, so these are CFAR 10.1 and ImageNet v2. So the way these data sets were collected is exactly the same process as the original data set, CFAR and ImageNet, but they were just collected later on in time. So these are like much smaller shifts. And for these shifts, fine-tuning does better. Another thing is what happens if we use worse features, right? So if we use an older self-supervised model that gets about 10% lower accuracy on ImageNet, in this case, fine-tuning does better because it's able to improve the features. So this work is part of a broader trend of lightweight fine-tuning. So it's a somewhat more general pattern that's been seen in the last year or two, besides just this work. So often, many works have found that, this message. How do you quantify the degree of distribution shift? Yeah, so in our case, we actually don't have a quantitative measure. In this case, these two data sets are kind of very clearly small shifts because the data collection procedure was identical, and the accuracy drops are very small. And the other shifts are kind of clearly larger, like if you're going from sketch to real or across different countries, and the accuracy drops are much larger. So there's a clear separation in the accuracy drop and also way it was collected. But I think for many other cases, you'd need more fine-grained ways to measure that. So it would be hard to compare if FMO, the satellite remote sensing, has a higher shift or domain net has a higher shift. Cool. So other works have also recently seen that if you fine-tune the entire model, it doesn't do so well OOD. But if you maybe add like a prefix or tune part of the model, then you do better OOD. So it's kind of part of a broader trend of things. And we think that linear probing and then fine-tuning, it's a great start, but it's really simple. There's got to be something better. So we'd love to hear your thoughts and ideas. So as a summary of this work, we saw that fine-tuning can do worse than linear probing out of distribution. And we have a theory explaining why it can do worse. And based on the theory, there's a very, very simple fix that gets improved accuracy across the board. So first, just linear probe to learn a good head. And then after that, unlock the head and fine-tune the entire model. Cool. Are there any questions before we move to the next part? Great. So now let's switch angles and talk about pre-training. How do we get these models that have such good representations? And for that, I'll hand the time over to Michael.
Great, thanks, Ananya. So our next project is called Connect, Not Collapse. It's about explaining contrastive learning for unsupervised domain adaptation. This is work jointly with Kendrick, Robbie, Jeff, Tanya, and Percy, and Ananya and ourselves. Okay, so this work is in the unsupervised domain adaptation setting, where we have two domains. First, we have a labeled source domain. Here's the sketch image of a clock, and also an unlabeled target domain. Here's real images of clocks. And the goal is to get high accuracy on the target domain without labels from the target domain. In the classical approach for UDA, we train a model that maps images to representations. And then using the labels on the source, we train to get high accuracy on the source. And simultaneously, we try to match to the distributions of the representations of the source and target. So this classical approach is motivated by theories such as H delta H divergence. So in order to get good accuracy, the theory tells us that we want the source and target representations to be indistinguishable. So that motivates these approaches such as UDA-SS and also DAN, which is a domain adversarial training method. In this work, we're focusing on the pre-training framework for UDA, where in the first step, you pre-train on unlabeled data that's combined from both the source and the target domains. And there's no explicit merging of the source and target representations. And then you take this pre-trained model and in step 2, fine-tune it on labeled data on the source. And then finally, just use that fine-tuned model directly on the target domain. So we tested out this framework using contrastive pre-training as the pre-training method, SWAV in particular. And we find that it's competitive with other UDA methods, including Sentry, which is a self-training method, and DAN, which is domain adversarial training on multiple data sets, DomainNet, Living17, STL-CFAR, and Entity 30. And also, if we add extra unlabeled data beyond just the source and the target domains, so in DomainNet, we have other domains beyond the source and target, and also in Living17 and Entity 30, which are subsets of ImageNet, we can add all of ImageNet as unlabeled data. And if we add that extra unlabeled data, we find an even larger boost in the target test accuracy. So the conventional hypothesis here is that maybe contrastive pre-training automatically during pre-training merges the features across the source and the target in order to achieve low edge delta H divergence and thus good target accuracy. So interestingly, we find that contrastive pre-training doesn't bring the domains together. So to show this, we inspect the features learned by contrastive pre-training versus DAN by training a discriminator between domains or between classes. So if you train a discriminator between domains on contrastive features, you get 8% error versus DAN features where you get 14% error. So that means that the DAN features are more indistinguishable. If you train a classifier, a discriminator between classes on these features, DAN and contrastive learning are similar. So overall, we can see from this that pre-training doesn't produce domain invariant features, and the domains are about as far apart as classes in the contrastive feature space. So overall, we find that contrastive pre-training performs competitively with strong baselines such as Sentry, DiRT, and DAN, so self-training and domain adversarial methods. It does, instead of collapsing domains together like the classical UDA methods, it learns features that vary substantially across the domains. So the question is, why do these features still continue to generalize to the target domain without enforcing the domain invariance like the classical methods? So with this, I think I'll hand it over to Ananya.
Cool, thanks, Michael. So we'll start with some setup and explain what contrastive learning is, and then dive into the intuitions and a toy version of our theory, and briefly describe what our theoretical results are like. And then Michael will talk about our experiments where we test out predictions from theory on real models and data sets. So first, let's start with some setup and describing what contrastive learning is. So contrastive learning hinges on positive pairs. So a positive pair is two different augmentations of the same original input. So augmentations are things like crops. So two crops of a single image. And the contrastive objective has two parts. The first part is you take a positive pair, so two crops of the same image, and you try to map them to similar representations. The second part is you want to map augmentations of different inputs to different representations. So we can visualize this process using a graph. So in this graph, we have two domains and two classes. And the augmentations used in contrastive learning are very aggressive augmentations. So the crops, for example, often keep only 10% of the image. And we add things like colorization, Gaussian noise, etc. So these augmentations may not preserve the class or the domain. For example, imagine I have a photo of a large bear, and I take a small crop. The small crop might only consist of fur. And if you also add color, it might not even be clear which animal this came from. So in general, augmentations can take you between domains, and they can also take you between classes. And they can take you between domains and classes. So over here, alpha denotes the probability that an augmentation confuses the domain. Beta denotes the probability that it confuses the class. And gamma denotes the probability that you confuse both of them. Now, of course, a lot of augmentations do preserve the class and domain. It's still very clear that it's a butterfly if it started out as a butterfly. And so that probability is rho. So we call these things connectivity. So rho, alpha, beta, and gamma denote how connected different class domain pairs are by augmentations. So we can represent this augmentation graph using an adjacency matrix. So here are the different class domain pairs. Each class domain pair is a vertex, and the augmentations are edges. And the weight denotes the strength of the how likely the augmentation is to connect the pair. So we have an adjacency matrix where the rows and columns are the class domain pairs, and the entries denote the edges. So now that we've gone through that setup, I'll talk about our core intuitions for why contrastive learning can produce these features that work well on the target, even without seeing any label data from the target. So let S plus be the positive pair distribution. So these are two crops of the same image. And let PU be the unlabeled data distribution over all the unlabeled data. And let F be the feature extractor that we're trying to learn. So we first pre-train on all the unlabeled data. So we use a pre-training objective called the spectral contrastive loss. And that is two parts. So the first part is you take augmentations of the same image, X and X plus, and you map them to similar representations. And the second part is we take augmentations of different images and we map them to different representations. So we first learn F hat that minimizes the spectral contrastive loss. And this doesn't use labels from any domain. So it's done purely on unlabeled data. So finally, once we have F hat, we'll train a linear probe on the source domain, so using source labels. And without any target examples, without any target labels, we'll see how it does on the target domain. So we'll start out with a simple toy example where we can compute F hat exactly. So we can look at exactly what the pre-training process learns. And we can visualize these learned representations and see why you get generalization to the target domain. So let's start with this very toy setting. So we're looking at binary classification and one example per class and domain. So we have two classes, two domains, and 4 examples in total. So this is similar to the graph we saw before, except we have exactly one example in each class domain pair. And let F hat be a matrix where the rows are the learned features. So this is F hat. Each row is a feature for one example. So we have 4 rows. And each of the features are 3 dimensions. So recall that we had this matrix A, which is the adjacency matrix of the augmentation probabilities, the positive pair probabilities. And with a few lines of algebra, you can show that what contrastive pre-training learns is a low rank approximation of the adjacency matrix. So it's formally given by this minimizing the Frobenius norm of A minus F hat transpose. But intuitively what that means is you're trying to get F hat to be low rank, low dimensional, and it should approximate this big adjacency matrix. And a standard result in linear algebra then tells you that F hat is given by the top k eigenvectors of A. So what are the top k eigenvectors? Now this depends on the adjacency matrix. So it depends on the augmentation parameters, alpha, beta, gamma, and rho. So that's what decides what these top k eigenvectors will be. So the connectivity parameters, the augmentation, controls what the pre-trained features look like. And we'll see what happens to these features geometrically in the next few slides. So if all that math went by a bit quickly and didn't make too much sense, that's perfectly fine. We'll now show some pictures about what the representations look like in this simple toy example. So under this condition, where alpha and beta are greater than gamma, so what does that mean? So alpha is the probability that augmentations keep the class the same, but can change the domain. Beta is the probability that you keep the domain the same, but you change the class. Gamma is the probability that you change both the class and the domain. So what this condition is saying is that you're more likely to change one thing, either just the domain or just the class, than change 2 things, change both the domain and the class, which seems intuitive. It's probably not so likely that augmentations change both the class and domain as often as just one of them. So under this condition, the features learned by contrastive learning are disentangled. So over here, the butterflies are on the top, the clocks are on the bottom, the sketches are on the left, and the photos are on the right. And the magic is that this whole thing, these representations are learned without any labels. So now we have labels from the sketch domain, and we train a classifier. And because of this disentanglement, it extrapolates to the target domain and gets high accuracy without seeing any labels. And this condition on the augmentations is key. So in fact, what happens if this condition didn't hold? What happens if the augmentations are more likely to change both the class and the domain than just changing the domain? So in this case, if you compute what the features look like, they actually get swapped. So now if you train a classifier on the sketch domain, you end up getting the target domain wrong. So this condition on the augmentations is really important. So that was a very simple toy example, just to build some intuitions of what's going on. In our paper, we consider a stochastic block model. And this extends it to multiple domains, many classes, and many examples per class and domain. And so we proved that the same conditions that I just described allow contrastive pre-training to learn linearly transferable features. So it disentangles the source and domain. And if you train a linear classifier on the source, it generalizes to the target. And follow-up work by Jeff, Tungyu, and others has generalized this beyond random graph models. So you don't need to make these assumptions about edges being generated in a random way. And the graph can be very asymmetric, but it still works under these assumptions. The other thing we show is we give an example where contrastive pre-training can outperform ERM and DAN even when using the same augmentations. So contrastive pre-training can have different advantages from these other methods. It can solve scenarios which these other methods cannot. So now I'll hand the time back to Michael to talk about our experiments.
Great, thanks, Anaya. So in our theoretical results, the connectivity parameters govern how the test accuracy, the target accuracy will be for contrastive pre-training. And particularly, it requires the key condition that alpha and beta are both greater than gamma. So to test this empirically, we try to estimate alpha, beta, and gamma by training a classifier to predict between the augmented images between domains or classes, depending on which one you're estimating. And we'll evaluate that on how that examples. And so we'll fit a sort of a scaling law type thing, where we try to fit target accuracy as a function of alpha, beta, and gamma with coefficients W1 and W2. And we'll estimate W1 and W2 by fitting a linear function in log space. So if we do this and we compare, we look at the target accuracy of the contrastive methods, SWAV, MoCA V2, and MoCA V3, we find that the connectivity parameters give you a very high correlation with the target accuracy. So it predicts the target accuracy well, up to almost 0.8 R squared. And if you try to do the same thing to try to predict the target accuracy for non-contrastive methods like DAN and Sentry, we'll find that the correlation is much less. So either 0.3 or almost 0 for Sentry. So connectivity parameters explain the target accuracy for contrastive methods, but not for non-contrastive methods. So we also look at the geometry of the learned contrastive features, and we find that the class and domain are disentangled. So we do this by training a linear probe for class versus domain information in the contrastive features. So if you train a source class classifier and a target class classifier, and you look at their cosine similarity of the learned features, you'll find that they're very aligned for both Living 17 and DomainNet. However, if you train a domain classifier and compare those weights to the source classifier, find that they have very low cosine similarity. So they're kind of orthogonal. And we find a similar thing for the target class classifier. So we find that indeed empirically, class and domain information are disentangled in the learned features. We also run an experiment where we ablate the examples that are contributing most to connectivity between domains. And we compare that to just dropping a random subset of examples. In particular, we train a classifier to distinguish between the source and target domains. And then we ablate the examples that are near the decision boundary, so that are in between the two domains. And if we do that, we find that ablating those in-between examples hurts the target test accuracy for contrastive pre-training a lot more than just ablating a random subset of examples. Finally, we also look at the role of different types of unlabeled data, and we find that the target unlabeled data is most important. In particular, in this table, so the ERM column is just the baseline performance without any unlabeled data. If you do contrastive pre-training with the source unlabeled data, SWAB S, you actually find that it doesn't actually improve over the baseline. But if you do SWAB contrastive pre-training on the target unlabeled data, it brings us a lot of the way there to the overall contrastive pre-training method where you combine source plus the target unlabeled data. So to conclude, we found that contrastive pre-training is a competitive method for unsupervised domain adaptation. It works without collapsing the source and target representations. And instead, it disentangles the class and domain information, and that's what enables the transfer. And this nice geometry of the features is a consequence of the structure of the connections between the domains and the classes via the strengths of the data augmentations. Hand it back to Ananya now.
Excuse
me?
me?
Yeah.
Can I have a question on the last slide? Can you give us an example of what does collapsing example? Thanks.
Yeah, so in the classical approach to domain adaptation, you'll add this term in your objective where you try to confuse the representations from the two domains. So the goal is to make the distribution of source and target representations the same. Mm-hmm. And the intuition is that if you learn representations for source and target that are overlapping, then if you have labels now on the source, then it'll transfer better to the target. That's the intuition. Mm-hmm. But we show that you don't have to have this overlapping geometry in order to have transfer. Instead, contrastive pre-training works by disentangling the class and domain information in the features.
I see. So basically what you mean is that collapsing is one way to do transfer learning, but contrastive learning is another way and a competitive way to do transfer learning. Is this right?
Yeah, I guess disentangling is another way of doing it, and interestingly, contrastive pre-training doesn't do the merging one. It seems to disentangle the class and domain information instead.
I see. Thank you so much.
Yeah.
All right. So in the last part of the talk, I'll talk a bit about other interventions you can use to improve robustness. So I think pre-training and fine-tuning are really powerful ways to improve robustness. And it's kind of cool that it improves the OD accuracy so much when it's not tailored to the distribution shift. Like all we did is pre-train on tons and tons of data. And then you fine-tune in maybe a slightly smart way, like you can't fully fine-tune, you need to do this linear probe initialization. It's kind of amazing how general it is. To get further gains, I think you need to look at the type of distribution shift. right? So OOD is pretty broad. It just means that the train and test are different distributions. And so no one method will work universally across all distribution shifts, I think. And we've seen this in a few recent papers of ours. So in one paper, we benchmarked pre-training and prompting interventions in NLP across 23 data sets and 14 models. And we found that nothing was really very consistent. The results vary a lot depending on the type of OOD setting. So to develop principled methods, I think we need to examine realistic shift structures. And so in some of our work in the past, we've looked at things like what happens if the distribution is shifting over time. There's like a gradual shift that happens over time. How can you adapt to that shift? And so we found that self-training can do a really effective job in this case. Another example of a shift is spurious correlations. So maybe you have a feature that's very correlated with the label in the training domains, but it's independent of the label in the test domains. And so here self-training is again very effective. In the Connect Not Collapse paper that Michael and I talked about, there's also a key structure. And the key structure there is the augmentations. Right? So if your augmentations did not satisfy some important conditions, then pre-training won't help you there. So we've also done work on mitigating trade-offs. So often a lot of robustness interventions increase out of distribution accuracy, but at the cost of in-distribution accuracy. So they lead to a drop in distribution accuracy, which is not very desirable. And we've seen that there are two very effective ways to mitigate this trade-off. So in a paper with Michael, we showed that self-training on lots of unlabeled data can get the best of both worlds. If you have one classifier that does really well in distribution and another that does really well out of distribution, you can do a form of robust self-training to get the best of both. And another way we found that was very effective is to calibrate each model and then ensemble them. Finally, I think we also want to go beyond accuracy. So I think it's very important to have good evaluation schemes in place, which also look at things like fairness and homogenization. So in one paper by Eric Jones and other collaborators, we found that if you use this method called selective classification, you can get high accuracy, high average accuracy, but in minority groups, you can often get really poor accuracy. So I think it's very important to look at those kind of things. In work that Rishi did recently, what he showed was that if you train a bunch of models, like they may often produce very similar predictions. So if you have an algorithm that's deciding if someone should get a job or not, it might produce very correlated predictions across companies. And this is problematic because now all companies using the software might reject a person of a certain race or a certain nationality. Right? So you want some diversity in the predictions made by different models. And I think that's also something that's important to look at besides accuracy. Cool. So finally, some concluding thoughts about why we've been focusing a lot on pre-training and fine-tuning. So I think one big advantage of pre-training is that a rich organization can pre-train once, and now everyone can fine-tune for many tasks cheaply. And so this is in contrast with some of the other methods like self-training on huge amounts of unlabeled data. For that, every person would have to self-train on tons of unlabeled data. So pre-training is kind of very cheap for people to use once it's been pre-trained once. And this approach of pre-training and fine-tuning without any additional robustness interventions gets state-of-the-art on many robustness data sets. So it seems like a very effective and general way to get good accuracies. So in conclusion, in this series of works, we've shed some light on why pre-training on unlabeled data can lead to representations that are robust. And then we showed that naive fine-tuning may not use these representations very well, but if you fine-tune in a slightly smarter way, then you get large robustness gains. And this pre-training fine-tuning paradigm seems very general and seems to work quite well across the board. And if you want further gains, you can dive into the distribution shift and see what it's like and get good methods for that. Thank you.
Thank you for Anaya's Michael's great talk. Hi audience, do you have any questions? Please, you can open your mic to talk. Basically, I have a question in terms of the fine-tuning. Like in your previous slides, there's a big company fine-tune one model, then all the small company can reuse it. This is basically like a foundation models, your group define it. One question is about security question is model stealings. For example, this is the fine-tuned model is a property of the big company, but it can be easily stealed by others, using a very cheap ways.
Okay.
Yeah. How do you prevent this? How do you comment on this? Yeah.
So just to get this right, you're saying that
you have to make it
easy to steal models with
you must steal the model's parameters for kind of like IPs. Like kind of I steal your model, treat it like my own. I don't pay you for fine-tuning my own things.
I see. So I'm trying to understand this a bit better. So do you think these models are easier to steal than other models, like models trained from scratch, or is there some intuition?
Exactly.
Why is it easy to steal?
Why I say so? Because the big company actually use a large resource to train a foundation model.
Okay.
Like a big data and train for 2 months to get my model. When this company want to make it to usable to other small company, they want to charge some fees. But suppose some small company don't want to pay for the uses.
I see what you're saying. So you're saying, why would the big company like make it available? Because then like you can just steal it. You can just steal the model. So
Exactly.
yeah, that's a great question. And I think some ways to get around that are like you maybe upload your code to the big company and then they'll fine tune for you. And then let you use that. So I think that's one approach. The other thing is maybe like, I think for a lot of these big companies, they actually don't make, like a lot of the ways they make money are like having access to users and user information and stuff like that, right? Which is kind of independent of the ML aspects of like whether they have a strong model. So that's why, so let's say Facebook, for example, like they've recently released some very, very big models, and it's probably not going to affect their profitability, because even if I had their model, I can't really compete with Facebook easily. Like I don't have the user base and stuff like that. So maybe Facebook just doesn't even care that much if we kind of steal their model. They're giving it out for free. So, but it just doesn't matter. It doesn't hurt their profits.
Yeah, that's good excuse. Yeah, I agree.
Yeah, it's an interesting question.
Yeah. All right. Yeah. So I just wondering some security issues they may happen because in this year's SAL, Nicholas did a job on the poisoning the contrastive learning. The very few instances can make the contrastive learning poisoned. This foundation model become dishonest on some point.
Yeah.
Like injecting a Trojan. Yeah.
I think that's a very important thing. Like so far in this talk, we've talked a lot about why foundation models are, let's say, good for robustness, but they also introduce risks.
Yeah.
Like data poisoning is one you mentioned. Like if you poison the foundation model, now you can poison everyone's models.
Right.
Yeah, and I think Rishi's work on homogenization also tries to investigate how centralizing all this power in a foundation model can be bad in some ways. Like if everyone's building off the same foundation model and it has some biases, like it's biased against certain types of people, then now
Exactly.
everyone's applications are biased.
Right.
So now
Right.
let's say you have a bunch of companies that are using a foundation model for hiring. And if the foundation
Right.
model is biased against people from some country, then now all companies are biased, right? And that person just can't get a job anywhere. Whereas in practice with humans, every human has their own set of biases and there's a diversity. So at least you may not get a job with someone who's biased against you, but you get a job somewhere else. So this centralization of power, I think, like you're saying, it introduces security risks. It could introduce risks around bias and fairness. I think it's important to mitigate these.
Right. Right. The bring benefits also bring risk.
Yeah.
Got it. All right. So is there any further question popping up?
Excuse me?
Yeah, please.
Excuse me. May I have a question about the butterfly and the clock example, the adjacency matrix of alpha, beta, gamma? Yes, just this one. I'm wondering if your analysis carry over when the alpha becomes alpha butterfly and the alpha clock, because for different different classes, they might have different portion of distortion. So can your analysis carry over? I see.
Yeah, that's a great question. So for example, here in this adjacency matrix, we have like 4 alphas, right? We have clock to clock, like real clock to sketch clock, real butterfly to sketch butterfly. They're both alphas. So actually it doesn't require this. And Jeff's recent follow-up paper, it proves it under much more general conditions. It doesn't need these symmetries. But the symmetries make the calculations, like in this toy example, with these symmetries, you can compute the exact representations. That's a little bit harder if there are asymmetries. You need to do a bit more, you need to use some more sophisticated mathematical tools. You can't just compute the representation in a closed form.
I see. Because using just alpha, beta, gamma is very clear for demonstrating the idea.
Exactly.
But what I ask is the generalization of this method.
Yeah.
So may I have the follow-up paper?
Yeah, it's maybe I'll find it. So this is paper. It's called Beyond Separability, Analyzing the Linear Transferability of Contrastive Representations to Related Subpopulations.
So it's beyond separability, right?
Yeah. I can share.
Thank you so much.
Yeah, of course.
Thanks.
Yeah, and just to be clear, so there you would probably, the condition is roughly you'd need both of these alphas to be greater than both of these gammas.
Yes. I understand, because when the values are diverged, you need to make some more assumptions.
Yeah. So it can be asymmetric, but you need both of them to be greater.
I see. It's basically a generalization of some of your slides, the conditions in some of your slides, right?
That's right. Yeah. The conditions are generalized. Yeah.
Thank you so much.
Yeah, of course.
All right. So if there are no further questions coming up, this is the end of today's seminar. Thanks again for Anaya and Michael to give us great talks. When you come to Tokyo, please visit our center at Nihonbashi office.
Yeah, and let us know if you're at Stanford.
Sure.
Yeah, same here. Thanks a lot.
Yeah.
Sure. All right. Bye-bye.
See you.
See you. Bye-bye.
See you.